Hello, welcome. We will discuss today a special kind of design called placket Berman designs. Let us see the topics, the contents of today's presentation, introduction, then construction of placket Berman designs, how we will find out alias matrix in placket Berman design, and then how to analyze the data that are resulted out of the experiments using placket Berman design. So, placket Berman design was developed by Placket RL and Berman JP in 1940 and 46. This kind of design is used to study k equal to n minus 1 variables where n is multiple of 4. So, let the number of factors be factors to be studied is k and the number of experiments is n. So, placket Berman design is used when k equal to n minus 1 when n is power of 2 like 2 to the power 2, 2 to the power 3, 2 to the power 4, then this placket Berman design or PB design is equivalent to fractional factorial design. Okay. But there are some cases when that n will not be a power of 2, not be power of 2. For example, if n equal to 12, this is not power of 2. Okay. So, when n is not power of 2, so in that case this is a special design and placket Berman design is applied for such situations. So, n equal to 2, 20, 28, 34. So, this kind of design, these are the most popular one for placket Berman design. So, in placket Berman design often the main effects are of interest. Main effects. So, we are not interested in interaction effects. Interaction effects, whether it is 2 OA interactions or more, this is not of interest. Okay. So, it uses standard orthogonal arrays, Okay. Another interesting issue here in placket Berman design is that when we use fractional factorial design like 2 to the power k minus p design, suppose you are using 2 to the power k minus p design, for example, 2 to the power 3 minus 1 or 2 to the power 6 minus 2, whatever may be this resolution 3, here resolution 4. So, what happen? You have generators, so equal to p and defining relations equal to p plus 2 to the power p minus 1. But in placket Berman design or the design where placket Berman design is what I can say valid. So, they or used, mostly used, I cannot say valid, mostly used. So, there the defining relations are not available. That means, if I use 2 to the power 3 minus 1 3 design, then you have seen earlier the defining relation I equal to A B C, and you know that how to now obtain the 2 to the power 3 minus 1 design and conduct the experiments. But in this case, in PB case, placket Berman case, this defining relation are not known. Okay. So, what happened, the alias structure cannot be found out by knowing the defining relation and then multiplying every factors. So, you require regression approach to find out the alias structure. Okay. As k equal to n minus 1, and this is basically the case where PB is used. So, you see that there will be no degree of freedom available, there will be no degree of freedom, degrees of freedom available for error to be estimated. If situation is like this, error cannot be estimated. So, what you require then, if you use k less than n minus 1, then depending on the type of effects is of interest. So, there can be some source of error estimation. Okay. So, we will discuss those things. And another important one is that if you go for 2 to the power k or 2 to the power k minus p design, you will find out that this design can be represented in terms of cubes, but this placket Berman design where n equal to 12, 20, 28, 34, you cannot represent that in terms of cubes. So, as a result, this type of designs are known as non-geometric design, non-geometric design. So, with this, let me read out from the slide. So, it is developed by Placket and Berman in 1946, used to study k equal to n minus 1 variables in n runs, where n is multiple of 4. If n is power of 2, Placket Berman design are identical to the power k minus design. For n equal to 12, 20, 24, 36, PB designs are of interest. Only main effects are of interest. PB is standard orthogonal arrays. There is no defining relations as interactions are not identically equal to main effects. When k equal to n minus 1, no degrees of freedom are available to estimate error terms, as Placket Berman designs cannot be represented in cubes. They are sometimes called non-geometric designs. Okay. Now, second is that how do you construct Placket Berman design? Placket Berman design or PB designs also utilizes two labels, label high or plus, low or minus. Trial experiments are assigned plus or minus signs in a cyclical manner. Okay. So, what is this cyclical manner? So, just you assume that there are 7 factors A, B, C, D, E, F, G. Also, you say that the trial 1 can be conducted keeping A at high, B at low, C at low, D at high, E at low, F at high and G at high. Then, to maintain the cyclicity, your next trial will be started with plus, then minus. Suppose what you are doing then, where you are ending, in the first trial you end with G plus. So, this will be, this plus sign will start in the next trial first, followed by the again the from the remaining signs from the left. Okay. So, what do you mean? You have started with first a plus, then minus minus, then plus, then minus, then plus and plus. So, 1, 2, 3, 4, 5, 6, 7. So, okay, it is k equal to n minus 1, where k equal to 7. So, obviously, n will be 8. So, there will be one more row. Fine. So, first A you start like this. What will be B? B will, where you just see the 7th case run. So, 7th it ended with plus, you start with plus here. Then you repeat from here. So, then plus plus, then 2 minus minus minus, then again plus, then minus, then plus. Okay. So, what I mean to say here, I think I have given it a little differently. You just write down in this manner. Suppose I have A, B, C, D, E, F, G, 7 factors. Okay. So, my trial 1. So, actually this is my trial 1 and this one is trial 2, that is what I mean to say. So, in trial 1 you see ultimately A is plus minus minus plus minus plus minus minus plus minus plus plus, and the second one will start from here. So, plus, then you start from here, plus minus minus plus minus plus. Okay. So, in this manner, this is what is I am saying, that when the first one ends, second one start, and you repeat this process. Okay. So, as a result, what happened? I say this is my trial 1, this is my trial 2, then trial 3, then trial 4, trial 5, 6, 7. Okay. So, you see that trial 1 started like this, A, B, C, D, F, G, and trial 2 like this. Then you this cycle order you complete, and ultimately you complete up to 7. Okay. So, then what will happen ultimately? You see in the first trial how many plus? 1, 2, 3, 4, and how many minus? There are 3, 4 plus and 3 minus. Okay. So, you repeat this process, and then for the up to 7th and for the 8th run put all minus. Let me repeat, forget about this, here is some notation difficulties. So, you have 7 factors, you started for the trial 1, that means the first experiment, and you are keeping the factors either positive or negative. Suppose this is a start. Then for the second one, what you will do? You start where you end, you start from there and continue from the previous in sequence. Third one, in the same manner, start where you end and repeat this process. In that process, what you do? You finish the first 7 experiments, then the last one will be all negative, all at low levels. So, what happened? This gives you 28 plus signs and 28 minus signs. Here we have k equal to 7, there will be for each factor there will be 4 number of plus and 4 number of minus if you do this. So, 4 number of plus, and so all together there will be 28 plus and 28 minus with reference to this example k equal to 7. Now, question is that how do you start with this, why this one plus minus all those things. So, okay, that orthogonal array and concept and all those things are used, and but ultimately Placket and Berman PB they have given some starting trial designs, and the procedure is this. Once you there may be different combination, but please make it that it will be orthogonal arrays, and then once you start with the first trial, first experiment you do, the second experiment will be done in maintaining the cyclicity, and followed and third experiment, fourth experiment, like this k equal to k number of that experiment first. And then the last one, what will happen? The last one will be all the factors at low level. Okay. And this ensure orthogonality, this ensure that there will be equal number of high and low value per factors, and it is basically least number of experiment is required. So, all those things makes this PB design very popular. Another one is that your in this case it is not a 2 to the power type of experimental runs, it is other than that 2 to the power case. Okay. So, let us see some useful designs given by PB, that for k equal to 11 you require 12 experiment to be run, and the first trial is given like this. So, you use it to find out the second, third, fourth, like this there will be 12 trials, and then k equal to 19, k equal to 23, k equal to 35 and k equal to 27. So, these are the starting points given. So, when you start using Placket Berman designs, it is you first know that what is the number of factors and what is n value you want to choose, and accordingly you select one of the initial trial first trial from this the given plus minus signs, and you follow the cyclic process and get the complete design. Okay. This is what is presented here. You see here we have 11 factors, and that means we require minimum 12 runs. So, what you have done, you have run number 1 to 12 and this side 11 factors. Now, the first trial plus minus plus minus 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 plus 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 minus plus. Okay. Suppose this is what is the things you have started with. Then the second one will be where you have ended with plus. So, plus, then you start from this, then plus plus, then minus, then again plus, then 1 2 3 minus, 1 2 3 minus, then 1 2 3 plus, 1 2 3 plus minus. So, here you ended with minus, you start with minus again. Okay. So, minus, then again start from here plus 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 plus, 1 minus, then 1 plus, then 3 minus, then 3 plus. So, like this. So, in this manner you go like this and up to how much k equal to 11, up to 11 factors here you continue this. Okay. Then the last one 12th one you see all are negative, that means all at low level. So, now if you see every column of the factors a to k, you see there are equal number of plus and equal number of minus. Here plus, that means 6 plus 6 minus, every column like this. Now, if you take the dot product of the every column, what will happen? Dot product of any two columns you will get 0. So, plus means plus 1, minus means minus 1, that is the orthogonality. Okay. So, in this case few more issues to be discussed. We have how many factors? 11 factors. So, how many main effects? Main effects will be 11. How many two-way interaction effects? Two-way interaction effect will be 11 C2. How many three-way interaction effects? Three-way interaction effect will be 11 C3 and so on. but please keep in mind that placket Berman design is used mainly to get the estimate of the main effects. So, that means the second 3 and higher order addition they are also negligible, and we are 2 and higher order are negligible or of not interest. Okay. But from our previous knowledge of fractional factorial design, that we know that there must be defining relation to get the alias structure. So, in this case there is no that equal sum with because the main effects are aliased with second order interaction effects, and in earlier case we have written that main effect, suppose A is aliased with second order, suppose B C, in that case we will write like this, but in this design that kind of equal that alias structure aliasing is not there and or may not be there, and so as a result what happened, you will not get defining relations. So, I equal to A B C kind of things you will not get. Okay. So, we use regression approach to get the alias structure. Now, see here there are 12 runs and every main effect is partially aliased with every 2 interaction effects not involving itself. In this design the thing is that if you find out the alias structure of A, then A will be aliased, partially aliased in the sense that with other second order interaction effects which do not involve A or where A is not there, A is not into consideration. So, that means the AB interactions for example, the AB interaction is aliased with the 9 main effects involving C, D, E and K. Okay. So, furthermore, each main effect is partially aliased with 45 2 factor interactions. Now, let us come to let us see that how this kind of alias structure is generated. I told you in one of the previous lectures that regression approach to identify the alias structure, there we have given you the alias matrix. What we have done? We have run a partial model involving x1 factors and another maybe x1 is basically n cross p1 number of factors, and another one x2, another one full one involving x1 and x2, where this equal to n plus p1 and this equal to n cross maybe k minus p1, that if there are total number of factors. Otherwise, you write p2 the other effects. So, p effects and p2 effects. So, that means there is a model which is basically run, and there will be that is basically chosen, and there will be another model which may be a full model or the correct model. And then we found out here what happened, the estimate is beta 1 for all this, and let here it is beta 2. Then for the full model this will be with reference to beta 1 x 1 plus beta 2 x 2 y equal to plus epsilon. Now, we have computed expected value of beta 1 cap, and then what we have found out? We found that this is beta 1 plus A into beta 2, where A is the alias structure. So, this is nothing but x 1 transpose x 1 inverse x 1 transpose x 2, where x 2 coming from the Dijon matrix of here and x 1 is the Dijon matrix is this, that we have discussed earlier, and using this we have found out the alias matrix here. Now, because there are 11 factors, it is a huge one. So, we have used Excel sheet to find out this one. You see A to K, that what is this is what is basically, and again 1 to 12, this is plus 1 minus 1, this is what the Dijon matrix, and from here you can compute also A, B, C, all those things. So, there will be so many interactions, second order interactions. We are not considering the third or higher order interaction, because PB design is not for that purpose. Now, what happened, this is x1, then we computed x1 transpose, and then finally x1 transpose x1, when you do, you are basically getting this matrix, diagonal elements are 12, off diagonal elements are 0. Okay. So, if you develop a regression model using this x1, so this is the model you have chosen, this is the model where only the main effects are involved. Now, if you go for a full model involving all the interaction parameter, then x2 part will be this, that only the second order interactions. Now, when you multiply these things with, let me go back, x1 and x2, x1 transpose x2. So, ultimately you will be getting this kind of data, see 0 0 4 4, all those things. And finally, I will show you that when you find out the alias structure, you will be getting this kind of things. Here you see that minus 0.34 means it is basically 1 by 3. So, this is what is the alias structure computed using regression. And if you see the if you go back to the presentation now, you see that the A minus 1 by 3 BC, 1 by 3 we are saying 0.34, minus 1 by 3 BD, minus 1 by 3 BE, and like this. So, this alias structure is obtained using regression approach. So, you just see that using Excel and under this situation you will be able to find out the alias structure. Okay. So, only alias structure is not sufficient, you require to find out the effect as well as the sum square, and as well as you want to analyze the data, you want to find out whether the effects are significant or not, and which of the effects are significant, that also you want to find out. So, now effect is the same formula and SS is same formula what we have identified or what we have shown to you earlier. Now, when k equal to n minus 1, no degrees of freedom are available to estimate the error term, hence no significant test is possible if you have k equal to n minus 1, that is the situation. But if you have k is less than n minus 1, suppose actually you have 7 factors and you are going for 8 design, then you have no degree available for apart from the main effects, estimating other effects including the error terms. But if you use suppose k equal to 7, but you are using n equal to 12 and you are interested only in main effects, then you have 5 different runs available, and that will help you to identify the errors, provided the second and higher order interactions are negligible. So, under such situation, how the placket Berman design is used? Placket Berman design is used using dummy factors. Okay. Then what you do? Suppose you have okay, I will give you one example later on. Then once the dummy factors are known, and then find out the sum square for the dummy factors, and the sum of sum square or average of sum square of the dummy factors will be the mean squared errors, and degree of freedom will be the number of dummy factors. Then what happened? You have the main effect estimates plus you have the error estimates. So, you are in a position to develop ANOVA table and then find out the significance. Okay. So, here is one example. Suppose you have 4 factors. So, if you go by k equal to n minus 1, then k equal to 4 means you require 5 runs. But here what happened? You are using suppose 8 runs. So, you have 3 excess runs. So, that means you can use 3 dummy factors. So, this is one such design where A D1, B D2, C D3, D and this kind of structure is or layout is used, and you have used placket Berman that design that cyclic one. And once you have done experiment, let the result is like this. For the first treatment 10, second treatment 9, 10, 9 like this. Okay. So, what you do, you find out the effect using the formula 2 into contrast by n, and sum square is contrast square by n, and then you using this data you will be getting effect equal to this. For A it is 1.75 and like this, and SS also like this, and then what happened, you can find out, you can use this information to find out the error values. So, in this case let me repeat, PB requires k minus equal to n minus 1, as k equal to 4. So, we require 3 dummy factors D1, D2, D3, because we have used 8 number of runs. This one I have taken from internet material, source is this, and you can download and read it. So, now using this information SS and the degree of freedom, so we have computed the ANOVA table. You see the ANOVA table, we are interested in the main effect, we are saying the sources are the main effects only, and then A, B, C, D, the SS what we have computed, that is shown written here, and for error the SS of all the dummy factors. So, dummy factor D1 SS is 1.125, D2 0.125 and D3 0.125. So, if you add them 1.125 plus 0.125 plus 0.125, so ultimately you will be getting that 1.375. So, as every factor is having 2 levels, the degree of freedom available per factor is 1, but here error is equated to 3 dummy factors having 1 degree of freedom each. So, total degrees of freedom available for error is 3. So, now then using that additional ANOVA procedure, find out the mean square, which is sum square by degree of freedom, and then your MAC is 0.458. Then find out F value is MS, that effect by MS error, that means for A it is 6.125 divided by 0.456 is 13.37. In this manner the F values are computed. Now, from the theoretical value using alpha equal to 0.05, F13 is 10.13. So, you see, if you see the F value for all the 4 main effects, you find out that only A, F value for main effect A is more than the theoretical value. So, effect A is significant and other effects are not significant. Okay. So, this is what is placket Berman design. I hope that you understood it and you will be able to reproduce the same thing or recall this procedure whenever it is requested for. Thank you very much.